Okay, so there are other methods to solve this problem. So we are looking at to solve this problem, right? So before moving forward, let's define what graph Laplacian is. So a graph Laplacian is defined as a symmetric matrix. Let's say we have a graph of size V, and this has a V by V matrix, symmetric matrix representing the Laplacian matrix. It is on its diagonal, it has the degree of each corresponding node, and off-diagonal terms are 0 if two nodes are not connected, and they are -1 if two nodes are connected. So we can write that in index notation. This is what we will get. So this is a Kronecker delta. If ij are not equal, it is going to be 0. If it's equal, so we will have EIs as the diagonal terms of our Laplacian matrix. We can rewrite this in matrix format, and this relation is what we will get. So we have our Laplacian equal to degree matrix, which we basically discussed in the first class. It's a matrix with every element 0 except for the diagonal, and diagonals are just giving us the degrees, minus the adjacency matrix, which again, we have been working with since day one. So this Laplacian has some neat mathematical properties that will help us to solve many problems in undirected graphs, but these mathematical properties don't show up naturally for directed graphs. Unfortunately, it is an ongoing research to, extend different things coming from Laplacian to different operators on directed graphs, but we are not going to look at anything regarding the directed graphs here. So there are some properties for graph Laplacian. One is that the sum of all elements, vectors, basically columns or rows in Laplacian matrix is going to be 0. And we can show that easily. We have, so let's say that we are summing over j's in Lij. We write it in index notation. We separate these into two different sums. And if you look, this di doesn't have j. We bring this out. Sum over j of delta ij is 1 because it is only 1 if I is equal to j, except for that it's 0. So it's going to be di. And this guy, it is summing over j for ai. So it's summing over a basically row or column. It is going to be the degree, right? So sum of the elements in rows and columns of the adjacency matrix is always the degree of the corresponding node. So it is going to be minus di plus di equal to 0. So another property for Laplacian is that it has eigenvalues that are all non-negative. We can show that by saying that by writing the eigendecomposition in quadratic form, and then writing this quadratic form in index notation. So we have Vi, Lij, Vj, where V is elements, Vi is elements of our eigenvector, Lij is elements of our Laplacian matrix. And lambda is the corresponding eigenvalue. So we write Lij in terms of its index notation. Then we separate basically this into two sums. We bring Wij in. Now we write this guy as, we divide this by half. So we write it as 1/2 this guy plus 1/2 this guy again, right? And I and j have the same meaning. So essentially there's no difference in terms of symbols that we use, right? So I can say that I can flip the places of I and j here, and there's nothing that is changing, right? So again, delta ij times vj is going to give us vi. Delta ji times vi is going to give us vj. And we can write each of these in basically this format. And we are here saying that di again, the sum of all the columns and rows of the adjacency matrix are basically will give us a degree. So I can write the degree as a sum over rows and columns of the adjacency matrix. And then we have Aij in all these terms, 1/2 here. So I factor these Aij, right? And they are the same sums. I factor Aij, and I will have a quadratic relation here. I write it as Vi minus Vj squared. And then Aij, so this is a square term. It's not going to be negative anytime, right? And the other term is just the binary Aij, right? It's either 1 or 0. So there is nothing negative in this equation. And so we can show that the eigenvalue is always non-negative. And also we can show that we have at least one 0 eigenvalue in our matrix. And we can show it in 2 ways. We can say that we have essentially, we look at this relation and we say that, okay, let's say that we have, and actually we have an eigenvalue that is 0. So the corresponding eigenvector is gonna be, we can write it this way. So for this to be 0, we either need Aij to be 0, meaning that the corresponding points Vi and Vj are not connected, or Vi and Vj are equal to each other. So if two endpoints, so if two nodes are connected, their two endpoints should have eigenvector elements that are corresponding to them that are equal to each other. Oh, okay, but if we look at a connected graph, let's say that V1, V2, V3, V4, and we said that, okay, V1, V2 are connected. So their corresponding element on adjacency matrix is not 0. Therefore, their Vi and Vj, the corresponding elements of the eigenvector for these two nodes, should be equal to each other. Same for V2 and V3, same for V3 and V4. And if we write all these equations together, we will see that the elements, the corresponding elements of that eigenvector corresponding to eigenvalue 0 for all the nodes are equal to each other if those nodes are connected to each other. So if we have a connected graph, we will have basically an eigenvalue 0, and its corresponding eigenvector will be some vector with all elements equal to each other. For example, a vector of 1s. We can again show that by remembering the first property, that the sum of all values, all the basically elements on the rows and basically columns of the Laplacian are going to be 0. So let's say that I multiply L by a vector of 1s. It's essentially finding a sum over each row of L to find each element of the output. And it's always going to be 0 because I'm always summing, right? So when we write this, it is a dot product of each row of L, which with basically vector of 1s, which is always 0. So I will get a vector of 1s, which again shows that we have an eigenvalue 0. Okay, so let's look at some intuition into why this is called a Laplacian. So before going there, I need to introduce basically another concept in graph called incidence matrix. So let's consider this graph that we saw in our first session. And this has 5 nodes, and by sheer accident, it has 5 edges as well. So an incidence matrix is an E by V matrix, right? So essentially we have a matrix whose rows are corresponding to each edge in our graph, and if their columns are corresponding to each node in our graph. So it is 1 if that node is participating in the corresponding edge. So we have 2 ends, and in each row we will have 2 1s. So let's look at an example. So here I have a graph. It has 5 nodes, V1 through V5. It has 5 edges, V1, 2, V2, 3, V1, 3, so on and so forth. So we look at first row. We have V1, V2. So you're looking at this edge, and the corresponding nodes are V1 and V2. So we have 2 ones in this basically row. For the next row, V2, V3, we have nodes V2 and V3, a member of this. So we have this element, second row, and third column, second row ones, and everything else 0. And we can continue that so on and so forth until we get our incidence matrix. So we use this incidence matrix, for example, for projecting our, we looked at bipartite graphs, and we said that we can fold that to each of the sets, disjoint sets in that bipartite graph. And we can perform that projection using this incidence matrix, for example. So we looked at incidence matrix for undirected graphs. We also have oriented incidence matrix still for undirected graphs. And oriented incidence matrix is essentially assuming some orientation, some directions for basically every edge in that undirected graph. And it doesn't really matter what direction they have. At the end of the day, when we use it, you will see that they will cancel out and it won't really affect anything. But for the convention here, what we're going to use is that we're going to look at the index of the nodes, and we are going to say that the smaller I, the smaller index is going to get the +1 sign. The larger I is going to get the -1 sign. So for example, here, I want to fill the first row. I say that I look at V1, V2, right? This edge. And then V1 is smaller than V2, so I assign -1 here. I'm sorry, the other way around. So the smaller one, I'm assigning 1 here, and I'm basically assigning -1 to the index that is larger. So essentially at each row, we have 2 ones, right? One with -1, the other one with +1. The first one is always plus, the second one is minus. And this is just a convention, so it doesn't really matter because this is just some orientation that we're assuming on this graph. Now, let's look at, just remember the Laplacian in multivariate basically functions. So if we have a function f that is giving a scalar for each, let's say, point in this space. So let's say that we have multivariate input. We have, for example, an two-dimensional coordinates, basically, x and y, and we give that to f. It's going to give us the value of our function at that location. So it's going to map from R2 to R. Now, on this, we define Laplacian as the divergence of the gradient of that function. So gradient was essentially for each basically a function on a multivariate function. Gradient is finding the direction of the steepest ascent on that point in the space. So for each point, gradient of f is going to give us the derivative of that f with respect to different variables that we have. So derivative of fx, basically dfx over dx1 through dfx over dxn. What that means is that at each point, I'm looking at, again, how much change is happening between a node x and its neighboring nodes, right? Divergence, as opposed to that, it gets it a vector field, and it gives you some scalar. So the divergence of this is a dot product of this operator on basically that vector field. So it's finding the derivatives, it's summing over all the derivatives of that vector, right? That vector field with respect to different basically dimensions that we have, different variables, different input variables. And when we apply that divergence on the gradient, we will have Laplacian. So gradient was a vector field, which was showing how we are changing with respect to the next point to us. And this is it is considering a volume surrounding that point, and it is looking how many outflow basically flux we have at that basically volume. And so essentially, we are applying this to our gradient, and we are finding the second derivatives of our function f with respect to different variables that we had. So the same concept stands for graphs. For a multivariate function, what we had was an input x, which was, for example, two-dimensional x and y's, right? So for each point in the space, we were getting some scalar value. So that's how we define the function. Now on graphs, we will have each node, given each node basically in the graph, we will have a scalar. So it is mapping from our nodes to some real value. We looked at this example in the first session or second session. So we can represent a vector f scalar field essentially on this graph using this vector. So we can again define gradient as an operator on graphs as well. And in multivariate function, we were saying that we look at each point, we are looking how much we are changing with respect to points adjacent to us. So it is going to be the same for graphs as well. We are finding how much change is happening for each node with respect to the neighboring nodes. So if I have Fi represented on node Vi, I'm basically finding the difference between that and Fj represented on its neighboring node, Vj. And we're assuming that there is an edge connecting Vi and Vj here. And so if we want to show this using an operator, we can use incidence matrix. So again, so for the question you were asking, we just need to make sure that we're having the same order of edges. Oh, actually, I'm gonna show that for the next one. Yeah, that's for the next one. So yeah, so we are gonna have the same, because this is a 5 by 5, it just looks the same. But the output, right, is gonna have the same order of the edges basically as this guy. So if I want to apply this gradient operator, I can use the incident matrix. And I can say that I have the vector f, that is the values represented on the nodes on the graph. I multiply that by this incident matrix. And what happens is that each row, output row, is, so this is a 1, -1. These are representing two sides of an edge, right? Each row is representing an edge. If I multiply, it is finding the difference between two ends of an edge for all the edges in my graph. That's going to be my output. And that's what I'm looking for in the gradient operator. Now in divergence, I have, again, we were looking to the flux of outflux of the vectors surrounding basically point X in the space. So it is going to be the same for each node. I'm going to consider each node, and I'm going to sum over all the differences on the edges of that node. So I'm going to sum over basically different G's. Okay, so we call this vector G. And I'm going to sum over all basically elements of that vector right? That are incident to a particular node, and I'm going to repeat that for all the nodes in my graph. So if I want to have some basically operator, I'm going to use the transpose of the incidence matrix. Why? Because the rows were essentially showing what edges were connecting to a particular node, right? So for each edge, if that node was participating, we had a 1 in that column, right? If I find its transpose, each one is representing the edges. Now here is the edges. Here are basically the rows are nodes. And the first basically node, let's say V1, it is showing the edges that are incident to that node. So if I multiply that by our gradient, I'm gonna sum over all the edges that are incident, right, to that node. And that's gonna give us over Laplacian. And we will see that if we can show that if I multiply basically the transpose of the incidence matrix by the incidence matrix, I will get L, our Laplacian matrix. So again, the Laplacian matrix of the graphs is the divergence of the gradient of some basically operator. So it is divergence of the gradient operator. So that's the intuition essentially behind why this is called a Laplacian.